Hello everyone. In this lecture, we'll talk about the history of continents. Where did continents come from? How did the continent form? And what are the major mountain building events, also called orogeny, of the North America? So the first question is, where did the continents come from? At the very beginning, the Earth's history, there was no crust on the Earth's surface. The Earth was a hot magma mushy ball. As the Earth cooled from the surface, as well as from its interior, gradually, iron and the nickel elements sink deep into the core of the Earth, and the light elements such as the silica and oxygen left in the mantle. Cooling and crystallizing of the magma near the surface of the Earth further differentiate the magma. The crust became thicker as the surface further cooled. As the thickness grew, the mafic crust started to differentiate into intermediate and felsic crust, and the granite became a continent. At the beginning, the volume of granite was very small and scattered. There are two proposed mechanisms that explain how continents grew. The first is the magmatic addition. The subduction zone is where oceanic crust subducted underneath another plate, which can be continental crust or oceanic crust. The subducting plate introduced abundant sedimentary rocks that rested on the surface of the oceanic floor, which contains a considerable amount of water. When the plate subducted to a certain depth, the excessive of water makes the melt point of the subducting plate decrease and less viscous. The melt of the subducted plate introduced to the overriding plate generate a magma chamber and develop a volcano system on the overriding plate. The intrusion of magma chamber and the volcano system increase the volume of the continental plate. And if the overriding plate is an oceanic plate, it forms a magmatic arc on the plate. The second mechanism is accretion. Accretion usually happens at the convergent plate boundaries, at subduction zones. Fragmented buoyant crust and magmatic arc islands that are too buoyant to be subducted will be welded to the continental crust and contribute to the volume of the continental crust. When the subduction zone consumed all the oceanic plate, the two continents collided and sutured together along the thrust fault system. Accretion can also happen to the transform fault plate boundaries, where the fragmented buoyant crust or terrain in contact with the continent due to the lateral movement of the strike-slip fault. When the fault became inactive, the terrain will be welded to the continent and add volume to the continent. The major characteristic of the created terrains is that the origin, age, and lithology of the accreted terrains are different from the continent that they collided to. A good example will be the west coast of the United States. The areas shaded with yellowish and blue colors are the pieces of created terrains. From the legend, you can see that the created terrains are island arc, submarine deposits, ancient oceanic seafloor, and the continental fragments. Their origins and lithologies are different from the main North America continent. And that is also the main reason that we can differentiate them from each other and identify multiple episodes of accretion. After talking about where continents come from, how continents grow, now let's see how did we get the continent that we see today. What process are modifying the continent? There are two mechanisms modifying the continent, the Wilson cycle and the Ampere orogeny. The Wilson cycle describes the plate tectonic movements that open and close oceanic basins and their effects on the continent. A Wilson cycle starts with continental rifting and splitting into oceanic basins. A modern example is the Atlantic Ocean, which is continuously spreading and growing. When the oceanic plate at the passive margin cooled and became dense, subduction will initiate and develop the convergent boundary. The convergent boundary consumes the oceanic plate and the oceanic basin becomes smaller and smaller. A good example is the Pacific Ocean, where the ocean is closing. Closing the ocean basin will experience a creating magmatic arc, fragmented buoyant crust, sedimentary rock wedge, and deposited at the passive margin before suturing the two continents together. As the two continents sutured, mountain belts and high plateau will be developed, such as the modern Himalaya and the Tibetan Plateau. And this mountain uplift event due to a convergent movement of the two plates is also called orogeny. Once the convergent movement of the two plates waned, the mountain is eroded and the crust gradually becomes thinner. The continental crust is subject to enter another Wilson cycle. This is how continental drifting influenced the continent. Another way of modifying continents is empyrogeny. Unlike orogenies, empyrogeny does not cause a significant deformation to the continents. Empyrogeny causes uplift and subsidence of a continent in a large region, but relatively small amplitudes. Empyrogeny event can be caused by deglaciation rebounds of the crust, lithosphere heating from the mantle or mantle plume, as well as a cooling of the lithosphere. During glaciation, a large volume of ice is accumulated on land. Lithospheres subsided due to the excessive weight of the ice. Once deglaciation started, the ice volume reduced. The weight caused subsidence lifted. The lithosphere will rebound and cause uplift. The continent can also experience empyrogeny uplift if underneath mantle is upwelling or a mantle plume is located underneath, in which cases the lithosphere is heated. On the other hand, if lithosphere cooled, such as in the interior of the continent or at the passive margin, the lithosphere will experience empyrogenic subsidence and create basins. All these empyrogenic uplift and subsidence movement influence the large regions with small elevation changes compared to the continental modification caused by orogenies. This timeline shows the history of the continents. There were multiple episodes of supercontinents in the geologic past, and the most recent supercontinent was Pangaea. The following video shows the history of the continents.
The formation of these supercontinents greatly influenced modern geography, which in turn influenced modern civilization. So let's take a look at these continents of the past. Valbara. While only a theory as of now, the continent of Valbara is theorized to have been the very first continent. Forming around 3.6 billion years ago, a billion years after the formation of Earth, it was a supercontinent for the time, since it was, well, the only continent. Since it's so far back, very little is known about this theorized landmass. It's believed to have consisted of parts of South Africa, Botswana, Zimbabwe, and a small mass in northwest Australia. Ur is the oldest confirmed continent in Earth's history. At the time, 3 billion years ago, it was the largest continent on the planet because just like Valbara, it was the only one. Any other land was scattered as small islands across the global ocean. But since it contained most of the land on Earth, it was technically a supercontinent for the time, even though Ur was most likely smaller than Australia today. Ever since then, Ur has transferred from continent to continent for billions of years. What is left of Ur is split among India, Madagascar, and part of Australia. Colombia. Now we are starting to enter an age where we have slightly more evidence. The continent of Colombia formed 2.5 billion years ago. It's believed that the continent stretched 8,000 miles, or around 13,000 kilometers for you commies, north to south, and 3,000 miles, nearly 5,000 kilometers, east to west at its widest point. Rodinia. Keep in mind the span of time is vast. Rodinia lasted almost 500 million years. That's the rough equivalent since the beginning of multicell life itself until now. I can't spend the whole video saying what was where, but to put things into perspective, modern-day North America sat on the equator, Antarctica lay just north of Canada, and Australia north of that. 700 million years ago, Rodinia began to break apart. This breakup wreaked havoc on the Earth's climate and sent it spiraling into a global ice age known as Snowball Earth. Ice sheets span the entire planet, with the equator resembling modern-day Antarctica. It's believed these harsh conditions delayed multicell life until the glaciation passed. Pannotia. Even though Earth has existed for billions of years by this point and continents have come and gone, all of the land pretty much looked like this. And now we have reached multicell life finally developing in the oceans of ancient Earth. So congrats, life. Only took you a few billion years and 7/8 of the planet's history. Lazy bastard. Pannotia was located almost entirely in the southern hemisphere, hence the name meaning southern land. You could travel south from Canada down into South America, then just head straight west into Africa. And for the only time in Australia's life, it was on top of everybody. Gondwana. Gondwana was pretty much the central hub for the southern hemisphere lands, Australia, Antarctica, Madagascar, South America, and Africa, before South America decided to run off with that North American scoundrel. Gondwana stretched from the South Pole all the way to the equator. Gondwana saw the rise of arthropods, fish, amphibians, and reptiles in its 300 million year history. Global temperatures were far hotter than today, and so lush forests descended across the continent, even going down to the South Pole. Eventually, Gondwana would combine with another continent to form Pangaea. That continent was Laurasia. Laurasia was the northern counterpart to Gondwana. North America and Eurasia had clashed together, forming the Appalachian Mountains. The animals and plants that died on these mountains eventually became the coal which is mined today in areas like West Virginia. But millions of years ago, the continent Laurasia was divided between a massive Appalachian range, which in their glory days were the size of the Rockies. Laurasia is the simple combination of the two continents' names. Laurentia, the North American Craton, and a better continent name in my opinion, and Eurasia. Pangaea. Eventually the two great continents combined into a supercontinent we all know and love, Pangaea. Pangaea is seen as the genesis for what became our modern continents. When it died, the continents split and made their journey to the world we know today. Pangaea oversaw a catastrophic extinction which wiped out 96% of marine species and 70% of land species. But from this catastrophe came the dinosaurs, who wandered the vast continent. Throughout the age of dinosaurs, Pangaea began to break apart. 200 million years ago, North America and Africa divided apart, and the Atlantic Ocean was born. The northern Atlantic Ocean forming well before the southern. Around 150 million years ago, our good friend Gondwana split apart. Africa and South America split, leaving the distinctive puzzle piece shape we see today. Antarctica, Australia, and India all split apart from one another to become their own continents. 100 million years later, Europe and North America would finally divide, which means even after the death of the dinosaurs, Europe and North America were still one. India combined with Asia 40 million years ago, traveling the Indian Ocean for over 90 million years. In the vast history of Earth, our 7 continents are simply one moment in an endless ever-changing movement. Supercontinents may not exist today, but they will exist in the future. And perhaps future humans or other beings will think it was strange when the Earth wasn't just one continent. This is Cody of Geography Hub.
In the rest of the lecture, we are going to focus on the tectonic history of North America. The North America continent can be divided into 3 domains. The center stable craton consists of a Canadian shield and the interior platform. The Appalachian Fold Belt with adjacent coastal plain and continental shelf, and the Cordillera Fold and Fault Belts. The Appalachian Folded and Fault Belts was developed during Paleozoic, and the Cordillera was developed through Mesozoic and Cenozoic. So from the Wilson cycle, we can see that the North America continent was developed by colliding terrains and ancient landmass to the old stable Precambrian craton and the developing fold and fault system during the orogeny events. And this process happened to the east and the southeast coast of North America during Paleozoic, as well as to the west coast of North America since the middle Mesozoic till today. The center of North America continent consists of stable Precambrian craton, consists of a Canadian shield and a continental interior platform. It is relatively undeformed compared with the surrounding folded and fault belts. Within the craton, though not recent orogeny event disturbed the region, there are basins and domes formed by the amphiorogeny events, such as the Illinois Basin and the Michigan Basin, as well as the Ozark Dome and the Cincinnati Dome. The Appalachian Fold and Fault Belt was developed during the Paleozoic assemblage of Pangaea, when North America Laurasia collided with multiple terrains and the Gondwana continent. A large mountain belt and plateau in the size compared to modern Tibetan plateau was developed in the eastern and southeastern of North America. Later breaking up of the Pangaea led to the development of a coastal plain and a continental shelf at the outer rim of the Appalachian. Without a continuous compression, the Appalachian was left subject to erosion. What we see today is the remnants of ancient high Appalachian mountain belt. The Cordillera mountain uplift history is very intriguing. Subduction zone convergent boundaries develop mountain ranges near the plate boundaries. The North America Cordillera region extended way far inland. The Rocky Mountains are about 1,000 miles inland away from the west coast. How come the convergence stress at the plate boundaries can influence so far inland? There are two reasons, and both of them are related to the tectonic of the caldera. The North America caldera system was induced by subduction of oceanic Farallon plate. The subduction was at a normal angle at first, but later became flat subduction because an oceanic plateau on the Farallon plate was subducted and brought excessive buoyancy to the Farallon plate. The flat subduction of the Farallon plate caused the deformation further inland, and the Farallon plate later rolled back again caused more uplift in the continental interior because of the hot mantle upwelling related to the rollback movement. When the Farallon plate was completely subducted underneath the North America plate, the North America plate met the Pacific plate at where it used to be the mid-ocean ridge between the Farallon plate and the Pacific plate. The Pacific plate was young, hot, and buoyant. It cannot be subducted. The convergent plate boundary at the west coast became transform fault boundary. The transform fault boundary contributes less convergent force to the North America plate. The high elevation in the Cordillera region was too high and collapsed due to its gravitational potential when convergent stress reduced. The collapse of Cordillera made the North America plate extended, that the crust of North America in the region was thinned, and when the volume of the continent did not reduce, more area was added to the continent's surface in the North America plate. This additional area is added to the extension region, where is the basin and the range region of today, which led to the southern Rocky Mountains are further away from the west coast. This mountain uplift and extension of lithosphere in the North America lasted from the middle Mesozoic to late Cenozoic, and these processes modified the North America plate significantly. Now let's take a look at the global tectonic provinces. Similar to the North America plate, most of the continents have a stable craton center and surrounded by the deformed fold and fault belts. We can infer that the tectonic history of another continent may also in some degree be similar to that of the North America plate. Okay, so that is all about the history of the continents. I hope you enjoyed this lecture and see you next time.